In a busy chemical plant, a sudden high-pressure pipe leak is reported. Panic begins, and investigation starts.
Assalamualaikum everyone. Thank you all for joining on such short notice. So, I received a report that we had a serious pipe leak yesterday. High pressure line near the gorge. Production was nearly halted. We need answers.
Actually, I visited the site right after the report, and I think the pipe material was a high-grade stainless steel. So actually, it is unexpected and early failure.
True, but that section being under continuous pressure with chemical exposure. So I must admit that we haven't done inspection there in over 6 months.
That's a serious oversight. So what's wrong?
Okay, so from the scan, we noticed the spider web-like crack formation. So this is actually a clear sign of stress corrosion cracking.
So it's actually the result of high tensile stress combined with corrosive chemical, as you can see there. So it's actually very deceptive because we can't see it. We can see the damage until it suddenly fails.
So this could have caused major safety incident.
Absolutely. Actually, stress corrosion cracking doesn't give early warning. It is one of the most dangerous corrosion and mechanism in our environment.
So we have already isolated the line and begun the replacement. We also recommend adding corrosion inhibitors and adjusting operating pressure where possible.
Okay, so moving forward, we should consider our material selection because something better suited for our environment.
Understood. So let's revise our maintenance schedule.
Hey there! Ready for a story about why pipelines sometimes spill the beans? Or oil? Picture this. A pipeline, strong and shiny. But deep inside, it's facing a double whammy: stress and corrosion. Stress is like a bully, pushing and pulling the metal, making it tired. Corrosion. It's like rust's sneaky cousin, quietly munching away. When these two team up, the pipeline can crack under pressure. It's like trying to bend a rusty paperclip snap. Engineers call this corrosion under stress. Fancy, huh? So, to keep our pipelines in tip-top shape, engineers must play detective. They find the stress points and stop corrosion before it starts. And voila! No more leaks and everyone's happy. So next time you see a pipeline, give it a nod. It's got a tough job, but with a little help, it's leak-free and fabulous.
In this video, we'll look at the key factors and how to prevent corrosion under pressure. Corrosion under pressure, or stress corrosion cracking, happens due to stress, a corrosive environment, and weak material. The first factor is tensile stress, caused by pressure, welding, or mechanical load. The second factor is the environment. Exposure to chlorides, ammonia, or harsh chemicals speeds up corrosion. Some metals, like stainless steel, are more vulnerable to this kind of corrosion. High temperatures and long exposure times make corrosion happen faster. Corrosion under pressure is dangerous, but it can be prevented with the right strategies. Use materials that are less likely to crack, like duplex stainless steel or nickel alloys. These metals resist corrosion even under stress. Reduce internal stress through smart design and stress relief heat treatments after welding. Less stress equals less risk of cracking. Limit exposure to chemicals like chlorides and acids. Keep equipment dry and maintain a neutral pH to slow corrosion. Apply protective coatings, install cathodic protection, and inspect systems regularly to catch early warning signs. With the right materials, less stress, a controlled environment, and regular inspections, we can stop corrosion under pressure before it starts.
Let's explore the differences of stress corrosion cracking, SCC, versus other types of corrosion. SCC is caused by tensile stress and a corrosive environment. while other corrosion types are caused by chemical reactions alone. SCC needs stress for corrosion to happen. Other corroding materials do not require stress. Corrosion occurs naturally. SCC leads to sudden failures, while other types cause gradual loss. Appearance is different. SCC shows fine cracks, while others show rust or pits. Detection of SCC is tough until failure occurs, unlike others which are easier to spot. Finally, SCC is sensitive to specific environments, while others have wide-ranging impacts.
Corrosion under stress is analyzed rationally using empirical data and scientific theories. Let's explore its implications in engineering. Scientists and engineers use methods like stress-strain analysis and electrochemical testing to understand corrosion. These approaches help predict failures and develop preventive measures in structures and machinery. From a Naqli perspective, corrosion symbolizes spiritual decay. External pressures and weaknesses lead to moral breakdown. In Surah Al-Hadid, Allah reminds us of the transient nature of worldly materials, urging reflection on our integrity. Hadith emphasizes responsibility and trust, linking spiritual integrity to the safety and sustainability in engineering.
The following case study is an example of how engineered residual compression successfully mitigates environmentally assisted cracking in downhole components. This study focuses on stress corrosion and sulfide stress cracking. The United States alone produces 8.5 million barrels of oil and natural gas per day, relying on high-strength steel tubular products, including casings, pipes, and couplings for drilling and recovery efforts. Corrosive compounds like hydrogen sulfide and sodium chloride encountered downhole create a sour environment that can cause stress corrosion cracking, or SCC, sulfide stress cracking, and ultimately corrosion fatigue failures in drill pipe and casings. Couplings are particularly vulnerable to sulfide stress cracking due to high stresses imposed in directional drilling. These pictures show detailed views of environmental cracking in pipes and couplings. Three things must be present for stress corrosion cracking to occur: a susceptible alloy, corrosive environment, and tensile stress exceeding the threshold for cracking. Eliminating any one of these will prevent stress corrosion or sulfide stress cracking. Traditional stress corrosion cracking solutions generally address the environment or the material. Alloy substitution is possible in some applications, but generally expensive. Decreasing the steel casing strength reduces cracking, but limits allowed stresses, adversely impacting production. Coatings can isolate the environment, but have limited life and can potentially rupture, exposing the surface. A reliable, cost-effective method of mitigating failure from stress corrosion cracking is required to reduce operational costs and prevent potential environmental damage. This can be achieved by applying designed compression to eliminate tension, allowing the use of less expensive alloys in aggressive environments. At Lambda, we use designed compression to mitigate stress corrosion cracking and extend component life. Introducing a layer of compressive residual stress deep enough to contain surface flaws from pits or handling damage eliminates both stress corrosion and sulfide stress cracking without having to alter either the component material or design. Cracking is permanently prevented in sour environments for the life of the component. We use low plasticity burnishing to introduce engineered compression. LPB has been shown to eliminate stress corrosion and sulfide stress cracking in high-strength steels. By designing residual compression specific to each application, LPB provides superior protection for a fraction of the cost of crack-resistant alloys. In this application, a 40,000th or 1 millimeter depth of compression was applied with low cold working, minimizing general corrosion in addition to sulfide stress cracking. LPB performance was tested against hydrogen sulfide exposure per the NACE TM0117 standard. Both C-ring and full coupling specimens were used for this testing, LPB processed and untreated. All samples were composed of API P110 grade quench and tempered steel. Samples were submerged in hydrogen sulfide and pressurized to fractions of the specified minimum yield strength, noted as SMYS in the graphic. 720 hours without failure is the NACE standard to be approved for use in sour service. Loading for each sample started at 45% SMYS. If the sample lasted 720 hours without failure, the stress was then increased to 80, 85, and 90% SMYS for the C-ring specimens, and 80 and 85% SMYS for the full couplings. 85% SMYS is regarded as an aggressive performance test for coupling steel that is in direct contact with hydrogen sulfide. The untreated C-ring specimen failed in 10 hours at a stress of 45% SMYS. The LPB process specimens exceeded the runout life of 720 hours at all loads up to 90% SMYS. The untreated coupling failed under pressure at 45% SMYS after 37.5 hours. The LPB treated sample didn't fail and testing was terminated at 720 hours. A second LPB specimen lasted 720 hours at 80% SMYS. The pressure was then increased to 85% and the coupling ran for an additional 730 hours, after which the test was terminated without failing. All LPB treated specimens exceeded the typical hold time requirements at all loads in a sour service environment, proving that designed compression is effective in mitigating sulfide stress cracking.